Okay, so in this portion we are going to discuss another problem. It's not the least squares problem, a different problem in which pseudo inverse also naturally arises. Okay, it's called the min norm problem. Okay, so what is the min norm problem? So min norm problem essentially has to deal with when a system of equations Ax equal to b has many solutions, right? So typically the system Ax equal to b, as we know, it may either have infinitely many solutions, or it may have exactly one solution, or it may have no solution, correct? So when it has many solutions, then suppose I want to find the solution among all these that has the smallest norm. Okay, smallest norm. Okay, so I want to find the smallest of the x that satisfies Ax equal to b. Okay, and we'll use 2 norm as usual because that's the easiest norm to analyze in such things. Okay, so that's called the min norm problem. Okay, so of all the solutions to Ax equal to b, find me the one that is closest to the origin. Okay, that's the min norm problem. Okay, so as with the least squares problem, you can see that if A is square full rank, then this is very trivial. If A is square full rank, then Ax equal to b is satisfied by only one x, right? And that x is equal to A inverse b. There's only one x, so there's nothing to minimize over, right? There's only one choice given to you, and that has to be the answer, correct? Similarly, if A is A is skinny. If A is skinny, let's say, assume for simplicity that A is skinny full rank, then once again Ax equal to b may not even have a solution, in which case, there's nothing to minimize over, correct? This problem, we say that such a problem is not even feasible in this case, right? It's not feasible. Or it could be that Ax equal to b has exactly one solution, right? If A is skinny full rank, those are the only two possibilities, either exactly one solution or no solution. Again, if there's exactly one solution, there's nothing to minimize over, right? So this problem only makes sense when Ax equal to b has many solutions. So we'll just assume for this problem's purpose that A is fat full rank. Again, full rank assumption is to make things easy for us, as we'll see in a minute, and we'll relax the full rank assumption by involving pseudo inverse later on. Okay, so assume that A is fat full rank, and then let me try to actually find a solution to this problem. Okay, once again, the usual approach to solving this, there are multiple approaches to solving this. One approach to solving this is to use what are called the KKT conditions, right? And once again, these will be seen later in a course on, for example, optimal condition, right? That's the usual approach. You can take KKT conditions. The other approach is to actually explicitly write down all the solutions to Ax equal to b, right? So Ax equal to b, you can write down all the solutions by realizing that, well, if I find one solution to Ax equal to b, let's say x naught, and if I add any vector in the null space, right, u is in the null space, that will give me a solution to X equal to b, right? And then you do some manipulations and then try to convert it to a least squares problem and solve it. Okay, there are many issues with that approach. We'll explore this approach a bit more in the one of the assignments. Okay, but that's not of interest to us. What's again of interest to us is, as usual, the geometric approach. Okay, so let's try to take a geometric route to this problem. Okay, so I'm assuming A is fat full rank, so let's say A is m cross n, and my assumption here is that m is much smaller than n. Okay, so let us actually try to assume that, for simplicity's sake, for the geometric assumption, let me say that A is just like a one row vector. Very simple scenario. A is just one row vector, right? So it's just going to be like A1, A2 times x1, x2. This is my matrix A. This is my vector x is equal to b. Okay. I'm trying to look at all solutions of this, and among all these solutions, I'm trying to find the one that's closest to the origin. Okay, so you all know how this is going to look like, right? So if you have to plot this in the x1, x2 plane, so this is the x1 axis, this is the x1, x2 axis. Look at all the solutions to Ax equal to b, meaning all the points that satisfy this equation, right? That's just going to give me a line, right? That's going to give me a line, maybe a line like this. Okay, and of all the points in this line, I'm trying to find the point that has the smallest norm, meaning the point that is closest to the origin. So the natural thing to do is to, from the origin, to drop a perpendicular. Okay, something like this. Okay, and then this point over here, okay, is going to be my Ax star. Right? Sorry, This point is going to be my x, right? x1 star, x2 star. Okay, x star, the vector x star, the optimum x star is actually going to be this point. That's obtained by drawing a perpendicular, right? Because this line here represents the set of all x's, right? That satisfy this equation. Okay. Earlier, remember in the earlier scenario, we had drawn the plane, and every point in the plane represented ax, right? The set of all ax. So here I am just drawing the set of all x. Okay. So the solution is again very similar to what we discussed in the previous portion, right? For least squares, I just have to drop a perpendicular, right? And that perpendicular is actually going to give me the smallest solution. Okay, fine. Okay. So let us say that this point is x star. Then what must happen? Okay. So x star must be orthogonal. So this vector is x star over here, right? This vector is x star, right? Must be orthogonal to, so let's say this point is an arbitrary point x on this line, x minus x star for any x solving ax equal to b, right? Here this geometric intuition is given when A has a single row vector, but this can be generalized, and the intuition can definitely be generalized for an arbitrary A. Okay. Okay. So these are two things, right? 2, x star must satisfy ax star equal to b. Okay, so there are two things, right? So the first point is saying that this vector x star must be such that it is orthogonal to all the points along this line. Okay, all the vectors along this line. Okay, so any vector along this line can be constructed simply by taking an x here on this line and subtracting x star from it, right? So x minus x star is actually going to be this vector. Okay, this vector is going to be x minus x star. Okay, fine. So basically that's what the first point says. And second point actually says the trivial thing, x star must actually be on this line. Okay, so you must not have, for example, this perpendicular must not overshoot, right? So you must not draw a perpendicular like this and claim this point to be your x star. That will not work. Okay, so x star must satisfy ax star equal to b. Okay, so these are the things that we're seeing. Okay, so let's try to delve a bit deeper. What does it mean for something to be orthogonal to x minus x star? Okay, so what is this set x minus x star? What are all these x minus x stars, right? So what can you say about x minus x star? Remember, ax equal to b, x satisfies ax equal to b, x star satisfies ax star equal to b. So what is x minus x star do, right? Ax minus x star, what should it be equal to? Well, ax is equal to b and ax star is equal to b, so ax minus x star must be 0. Okay. Okay, so in other words, x minus x star is a vector in the null space of A. Okay, so if you recall your definition of null space, so point 1 can be rewritten as x star must be orthogonal to any vector in the null space of A. Any vector in null space of A. Okay, and the second point I'll write it as x star satisfies ax equal to b. I'll write as it is. Okay. Okay, so these are the two conditions that come from geometric intuition. Okay, so let's investigate the first point. How do we actually write an equation corresponding to the first point, right? Now, x star must be orthogonal to any vector in the null space of A. So what does null space of A mean? So null space of A means basically this matrix A, any vector in the null space is orthogonal to all the rows of the matrix A. Correct? It's orthogonal to all the rows of the matrix A. So basically, to pick a vector that is orthogonal to the null space of A, okay, you have to pick a vector that is actually in the row space of A. Okay, this comes from the very first segment when we discussed. We said that null space of A is orthogonal to the row space of A. Row space of A is IM A transpose, right? It's a linear combination of columns of A transpose or rows of A, correct? And we said that any vector that's orthogonal to null space of A must be in the row space of A. Okay. So this comes from is a consequence of the rank nullity theorem right from the very beginning, right? So the first equation is basically like saying that x star must be in IM A transpose, okay, or the row space of A. In other words, X star must be a linear combination of the rows of A. And you can see that if X star is like one of the rows of A, then it's definitely going to be orthogonal to any vector in the null space, because by definition this has to be 0, right? Vector in the null space has to make this product A times X to 0, okay? So naturally, by definition, every row is orthogonal to every vector in the null space, right? So X star must be a linear combination of the rows of the matrix A, okay? And it must satisfy AX star is equal to B, okay? So X star must be like A transpose Y, okay, for some Y, okay? That's what it means for it to be in the row space of A. Now I just substitute this equation in here, and then I get A times A transpose Y is equal to B. Okay. Once again, what we have here is A transpose Y is equal to B, and this matrix A transpose A is square invertible because of the full rank assumption, right? So if you go back here, we assumed A is fat full rank. If A is fat full rank, then A transpose is invertible, right? Once again, we discussed some of this in the first segment, right? So this is full rank, invertible, right? It's a square matrix. So Y is simply A transpose inverse times B, okay? And so what is X star? So X star is A transpose Y, which is A transpose inverse B, okay? So you can see what has happened here is that you get A transpose inverse here, this matrix multiplied with B. Once again, very similar. Earlier you had A transpose A inverse A transpose B, right? This was a solution to least squares. This here is a solution to min norm, okay? As you can see, A transpose A has become A transpose. The order has changed. All this to account for the fact that A is now fat full rank and not skinny full rank, okay? So this is the min norm solution to your problem, okay? Once again, this derivation is geometric, but you can actually give a very similar derivation using algebra. Okay, let's do that very quickly, just for completion's sake, right? Suppose X star satisfies these two properties, then I have to prove that it is a min norm solution by using algebra, okay? So X star has to satisfy these two properties. So let me just copy these so that I don't have to rewrite. So just paste it here. Okay. So now let us try to prove that it's a min norm solution, right? So to prove a min norm solution, what must I do? I must prove that for any other solution of Ax equal to B, for any x that satisfies Ax equal to B, that means any x that's a solution of Ax equal to B, I must have norm of x bigger than norm of x star. Okay, that's when x star becomes the min norm, right? Every other solution must have a higher norm than x. Okay, this is what I have to prove, right? So to prove this, I'll start from here, and then I will subtract x star and add x star, just like I did before. Okay, x minus x star plus x star, right? And once again, I'll take a square, okay, because for norms I need to take square. This will give you, just like before, norm of x minus x star square plus norm of x star square plus 2 times x minus x star transpose times x star. Okay, again this cross term is coming, by expanding the square. Okay, so now by point number 1 here, okay, x star must be orthogonal to any vector in the null space. This here, x minus x star is a vector in the null space, as we discussed before, and x star is orthogonal to that, right? So this must be 0. Okay, so what you are left with is basically sum of 2 squares. That means this must be greater than or equal to x star square. We are done with the proof. Okay, what's more, this once again, just like before, tells you when do you get equality. When is this going to be equal to this? When x equal to x star. That's the only possibility. So you'd say x star is the unique minimizer. It's a unique min norm solution to Ax equal to. Okay, what is x star here? X star is A transpose inverse A. Sorry, made a mistake here. X star is A transpose inverse B. Okay, Okay, A transpose inverse B. So that's your extra. It's a unique min-norm solution. Okay, fine. Now let us do a bit of manipulations that will actually lead to something amazing. What I'm going to do is here I'm going to plug in the SVD U sigma V transpose. As usual, let me assume this is a thin SVD, right? U sigma V transpose. Let me plug that in here. Okay. So A transpose will be what? U sigma V transpose multiplied by the transpose, which actually gives me V sigma U transpose, right? Inverse. That's what A transpose is, and there is an A transpose outside, which is V sigma U transpose. Okay. Right. So V, remember, is once again N cross R. Okay. V is like a tall matrix whose columns are all orthogonal to each other. So when you do V transpose V, you will get identity. By the way, it's important to mention that V transpose is not identity here, right? Because V transpose will not be identity, but V transpose V will be identity. I'll leave that as an exercise for you to think about. It's not very difficult. Okay, so V transpose V will be identity. So this term will go, and you will be left inside with U sigma square U transpose inverse, right? Which I'll simply write as U sigma power minus 2 U transpose. Okay, that's what I'll write. And then I'll multiply here, right? Multiply here, then you will get V sigma U transpose U sigma power minus 2 U transpose. Once again, U transpose U will be identity. Again, U transpose is not identity here. Okay. U transpose U will be identity, and here you will be left with V sigma to the minus 1 times U transpose, which is again pseudo inverse. Okay. So what you have obtained here, even though the expression looks very, very different, what you get here actually structurally just the pseudo inverse of the matrix. Okay. So what we are trying to say here is that the pseudo inverse of A times B is the min norm solution to Ax equal to B. Okay, is a unique min norm solution to X equal to B. Of course, assuming A is fat full rank. Okay, once again, this can be generalized, and I'm going to skip the generalization. No matter what A is. Okay, no matter what A is, even if it is not full rank, the pseudo inverse A pseudo inverse B will give you one of the min norm solutions. Okay, okay. So this is what you can summarize. You can say that A pseudo inverse B is one. The min norm is just right here, a min norm solution to Ax equal to B. Okay, a least square solution to Ax norm of Ax minus B whole square. Okay, so it's like a one-shot trick that solves both these problems. Okay, and it works no matter what A is, right? So you can actually just take pseudo inverse B. So if A is fat full rank, it will give you a min norm solution, right? If A is skinny full rank, it will actually give you the least square solution. Okay, if A is skinny full rank, the least square solution is also the min norm solution. Okay, that's clear, I hope, right? Because yeah. Okay, because there is a unique least square solution in that case. Okay, fine. So this is what the pseudo inverse tries to do. Okay, so one exercise I'll leave you guys with is you have already found the expressions for min norm solution and the least square solution. What are the corresponding minimum errors? Okay, so exercise, find the min value of least squares. Okay, meaning that in X here you substitute X. I already wrote an expression. Okay, and the min norm value. Okay, in terms of SVD. Okay, meaning that what I want you to do is if you look at the expression that we had written for the minimum value, I think we had somewhere here. Yeah, this is the expression that we had. I wanted to just plug in A in terms of its SPD. So A equal to U sigma V transpose and see what you get. Okay, and do a similar exercise for the min norm. Okay, so in the next lecture, what we're going to do is we're going to, by the way, these equations, especially for least squares, as I said, can't be written enough number of times. For least squares at least, they are called the normal equations. Normal equations, right? Okay. So in the next lecture, what I'm going to do is look at some algorithms to solve this problem. Okay, so it might seem like to compute this, all I have to do is compute the gram matrix of A, take its inverse, multiply and do it. But that's not computationally very efficient. Considering the importance of this problem, we have to look at efficient ways to solve it, which is going to be the topic of the next lecture. The lecture after that, we are going to actually look at the applications to data fitting. Okay, and we'll introduce the concept of linear regression.